Thank you. Thank you all for coming and staying towards the latter half of our research talks. I know it's been a long evening, but I promise if you lend me your ears for a little bit longer, I'll give you another gem to listen to. As the kind introduction that was offered on my behalf stated, I am a chemist, and like the other chemists in the room will attest, we spend our day-to-day work sitting around thinking about seemingly contradictory and almost impossible problems that seem that way from the outset. But if you take a fundamental understanding of the materials that we're working with and tweak them slightly, you can arrive at ingenious solutions. Take polybenzoxazole, or PBO, as an example. This polymer should be a household name. It's twice as strong as Kevlar, it weighs the same, and it's stable up to 650 degrees Celsius. For those of you like me that operate in Fahrenheit, that's the equivalent of incredibly hot. It's like 1200 degrees, much toastier than your oven. And yet, why isn't this not everywhere? Why aren't we using this to line our police officers' bulletproof vests or our firefighters' protective coats? Why is this not being used to protect satellite equipment up in space? It goes back to that contradictory problem. You see, PBO is incredibly strong, and because of that, it's hard to mold. How do you take something that's a rigid rod of plastic and flatten it out into a sheet? Or take it and other rods and weave them together to form a fiber without snapping it in the process? Well, I can tell you what the industry has done. The industry standard for PBO uses acids, like polyphosphoric acid, to soften the fiber, make it more moldable so they can form it into fibers. But as you can clearly see in the two circles up here, it's not just PBO anymore. There's acid contaminants left over that actively degrade the fiber. When the PBO fiber comes into contact with water, PPA helps to degrade it, breaking it and losing all of those desirable characteristics. So I and my lab mates, we sat around and we stroked our chins and thought, okay, how do we access the strength of PBO without dealing with the strength of PBO? Okay. We took it to the drawing board and we said, okay, here's the structure. Let's backtrack all the way back to the beginning, the most basic components, the monomers of the polymer structure. And we said, okay, if we do this correctly and use our lab's specialty, nanoparticle catalysts, little itty-bitty pieces of metal like copper oxide, we can take these precursors and through a series of chemical reactions, convert them into what we call pre-PBO. It's like PBO, but it has these little organic chains that hang off of it. And those organic chains play really nicely with common organic solvents and allow us to take our some 19,000 long unit polymer and make it completely soluble. And you might say, that's incredible, but the one PBO expert in the audience is like, hey, don't get too chuffed. The industry standard is 40,000 and you're spitting 19. How does it stand up to the industry standard? Well, thank you, knowledgeable member of the audience. But we took both of our polymers and we dunked them in boiling seawater, remember the water problem, for a week. And yet, our polymer, despite being less than half the length of the industry standard, came out on top with better strength retention and strength performance on par with the 40,000. So now, where do we go? Is the story's done, everybody pack up your bags, let's go home. No, right? What about our police officers and our firefighters? They still need protective materials. So I, and those who have noticed our research at NASA, have funded my research moving into the next year to solve that problem, to take our now soluble pre-PBO in its solvent form, lay it out to make a thin, controlled sheet, a coating that we can use to protect the people that need it, those here on the ground and those up in the stars. That's why my research matters. Thank you.